A Shell just built an electric car. And no, that sentence does not get less bizarre the second time you read it. One of the largest fossil fuel companies on the planet, a company that has spent over a century pumping oil out of the ground and selling it to the world, showed up in 2026 with a battery electric vehicle and told the automotive industry to pay attention. The question is not whether the car is impressive. The question is why a company that has zero history in vehicle manufacturing, zero showrooms, zero dealerships, and zero intention of selling you a car would spend the time, money, and engineering resources to build one. That question is exactly where this story begins, and the answer is far more interesting than the car itself. To understand what Shell actually did here, you need to understand what the company has been watching for the past decade. Shell has seen the same forecasts every other energy executive has seen. Electric vehicle adoption is accelerating. The internal combustion engine, the machine that made Shell one of the most powerful corporations in human history, is running out of road. The question Shell had to answer was not whether electrification was coming. That debate is over. The question was whether Shell would disappear with the combustion era or find a way to stay relevant inside the new one. What they built in June of 2026 is their answer. The car is called the Triple 10, and the name comes from three targets Shell set for itself. Sub 10-minute charging from 10% to 80% battery capacity, 10 kilometers of driving range per kilowatt hour of energy consumed, and a life cycle carbon footprint of 10 tons of carbon dioxide equivalent from production to end of life. Shell reports it hit all three. The charging test came in at 9 minutes and 54 seconds on a standard 175 kilowatt charger. The efficiency target landed exactly at 10 kilometers per kilowatt hour. The life cycle emissions estimate sits between 10 and 10.4 tons under specific testing conditions. Those numbers matter, but not for the reason most people think. Here is where the story starts to change shape. 9 minutes and 54 seconds on a 175 kilowatt charger is not what you would expect from a conventional electric vehicle. Most EVs at that charging speed take somewhere between 25 and 45 minutes to reach 80%. The physics of fast charging are brutal. When you push high current through a battery quickly, the cells generate enormous amounts of heat. Heat degrades battery chemistry. Heat accelerates aging. Heat, if left unmanaged, becomes a safety problem. To protect the battery, most manufacturers limit how fast the charger can push current into the cells. And that is exactly why charging is still one of the biggest complaints about owning an electric vehicle. Shell did not solve this problem by building a bigger battery or by connecting to a more powerful charger. They solved it by changing how the heat is managed in the first place. Inside the Triple 10 is a cooling system that looks almost nothing like what you would find in any production electric vehicle today. Conventional EVs use water and glycol mixtures to cool their battery packs, typically by routing fluid through plates or channels that sit against the outside of the battery cells. The fluid absorbs heat from the surface of the cells and carries it away to a radiator. It works, but the heat transfer is indirect. The fluid is never touching the cells themselves. Shell's approach is different in a way that sounds almost too simple. They put the cells directly into the fluid. The battery pack is submerged in Shell's dielectric thermal fluid, meaning the liquid is in direct contact with every cell surface simultaneously. Because the fluid is non-conductive, it does not short-circuit the battery. Because it is in direct contact with the cells, it pulls heat away far more efficiently and far more evenly than any plate cooling system can. This is the technology that the car was built to show. Not the car, the fluid. The Triple 10 was never a product. It was a laboratory on wheels, a proof of concept designed to demonstrate that immersion cooling can enable real-world EV performance that conventional thermal management simply cannot match. Shell's own documentation describes the vehicle as a groundbreaking proof of concept and the first roadworthy vehicle to demonstrate this single-circuit thermal management approach under real conditions. The word they use is demonstrate. They are not launching a vehicle. They are making a point to an audience that does not drive cars. They are making a point to the engineers and procurement teams at the companies that do. Think about what the single-circuit architecture actually means beyond the charging speed. In a conventional electric vehicle, you typically have separate cooling loops for the battery, the motor, and the power electronics. Each loop has its own fluid, its own pump, its own reservoir, its own set of hoses and connections and potential failure points. Shell's system uses one fluid to manage all three. Battery, motor, and power electronics are all cooled by the same dielectric fluid moving through one circuit, rejecting heat through one radiator. Fewer parts, less weight, less complexity, simpler manufacturing, lower cost per vehicle. These are not small benefits. In an industry where automakers are fighting for every fraction of a percentage point of margin and every kilogram of weight reduction, this architecture is offering something genuinely valuable, and it is being offered not by another automaker but by an oil company. Now ask yourself the question that Shell wants every automotive executive to be asking right now. If immersion cooling with a dielectric fluid allows a battery to safely accept higher charging current, that means you can potentially achieve the same real-world range with a smaller battery. A smaller battery means lower material costs. It means less lithium, less cobalt, less weight in the vehicle structure to support the pack. It means a cheaper car that charges faster and drives just as far. That is not a marginal improvement. That is a potential restructuring of the economics of electric vehicle manufacturing. The companies that figure out how to use thermal management as a design lever rather than an afterthought could build better EVs for less money. And if Shell's fluid and Shell's thermal architecture are what make that possible, then Shell does not need to manufacture a single car to profit enormously from every EV sold. This is the strategic move hiding underneath the engineering story. Shell is not trying to compete with Tesla, BYD, Volkswagen, Hyundai, or Mercedes. Shell is trying to become indispensable to all of them. The same way Intel sold chips inside computers made by a dozen competing manufacturers, Shell wants to sell thermal management solutions, dielectric fluids, EV greases, and cooling architectures inside electric vehicles made by every major automaker on the planet. The 1010 is a sales pitch, a very expensive, very sophisticated, very carefully engineered sales pitch, but a sales pitch nonetheless. Every performance claim in that car is a data point in a presentation being made to the people who decide what goes inside the next generation of electric vehicles. There is a history lesson worth pausing on here. When the California Gold Rush began in 1848, most of the people who got rich were not the ones panning for gold. The people who got genuinely, generationally wealthy were the ones selling picks and shovels and denim pants and supply stores to the people doing the digging. The miners took all the risk and all the effort. The suppliers took a piece of every miner's labor, regardless of whether that particular miner struck gold or went broke. Shell is reading from the same playbook. The EV race is the gold rush. The automakers are the miners, and Shell is quietly opening the hardware store. Here is the question worth sitting with as you think about where this goes. The immersion cooling concept is not new. Researchers and niche companies have been working on it for years, particularly in data center cooling where servers generate enormous heat loads inside tight spaces. What Shell has done is take that concept, engineer a practical fluid that works at automotive scale, and then build a vehicle to prove it works under real driving and charging conditions. The validation step is what matters. It is one thing to publish a white paper about immersion cooling. It is another to drive the car onto a track and film it charging from 10 to 80% in under 10 minutes on a charger that already exists at thousands of locations worldwide. That second approach gets attention in boardrooms in ways that white papers never do. Now consider the manufacturers who are paying the closest attention. Tesla has been working on its own thermal management improvements for years, and battery thermal design is a central part of what separates their vehicles from competitors in efficiency and longevity. BYD, which now sells more electric vehicles than any other company on Earth, has invested heavily in battery chemistry and pack design, but faces the same thermal limitations as every other manufacturer when pushing charging speeds toward the speeds consumers actually want. Volkswagen, Hyundai, Mercedes, and Stellantis are all navigating the same problem. How do you make EVs charge faster without destroying the battery? And how do you do that without adding cost and complexity that makes the vehicle unaffordable? If Shell can demonstrate that its fluid and architecture answer that question convincingly, the conversation with those manufacturers becomes very different very quickly. The life cycle emissions claim deserves a word of honesty here, because Shell is transparent about the conditions under which that number was achieved. 10 to 10.4 tons of carbon dioxide equivalent across the entire life cycle of the vehicle assumes a specific accounting methodology and, crucially, assumes the vehicle is charged on 100% renewable electricity. That is not the average American driver's reality, and Shell acknowledges it. The number is not a promise about what your EV emissions will look like in your driveway in Ohio. It is a statement about what is theoretically achievable with this architecture when the grid is clean. But even with that caveat, the smaller battery enabled by more efficient cooling does reduce manufacturing emissions, because producing battery cells is one of the most carbon-intensive parts of building any electric vehicle. A smaller pack means less of that burden regardless of where the electricity comes from. What happens next is genuinely uncertain, and that uncertainty is where the real story lives. Shell says its technologies are available today and scalable, but available and scalable are are not the same as proven at mass market volume with 10 years of durability data. Automotive supply chains move slowly. A fluid that works beautifully in a proof of concept vehicle needs to prove itself across millions of vehicles, in climates ranging from Phoenix in August to Minneapolis in January, in vehicles driven by people who may never change their cabin air filter, let alone monitor the state of their battery immersion fluid. Repairability and serviceability of an immersion-cooled battery in a dealership service bay is an entirely different engineering problem from building one in a controlled laboratory environment. The path from demonstration to adoption is long and full of obstacles Shell has not yet had to clear. But here is what is already true and already significant. An oil company that could have spent the last decade in denial about electrification instead chose to spend it engineering a solution that keeps them inside the value chain of the technology replacing their core product. That is not a small pivot. That is an existential bet made by an organization that employs hundreds of thousands of people and operates in almost every country on Earth. Whether the 1010's specific architecture becomes the standard inside future EVs, or simply becomes one of several competing thermal approaches, Shell has demonstrated something that most legacy energy companies have not. They are not waiting to see what the EV era looks like from the outside. They are trying to design a piece of it from the inside.